Okay, cool. So, the next question that we got on the menu today is asking us an alpha particle. And an alpha particle, if you are unfamiliar, is just a helium ion. So it's just two protons stuck together. That's what a alpha particle is. There on my periodic table, it's on the... so I'll open up my screen. So here on my periodic table, you know, on the upper right corner there is there's helium. That's what it is, and that's what an alpha particle is. And okay, so it's telling us it has a mass of 4u and moves in a circular orbit of radius 7.5 centimeters in a uniform magnetic field of 0.6 teslas, where the magnetic field is perpendicular to the orbit plane. And that has to be the case. Now we got to find the speed of the alpha particle, the period of the circular motion of the particle, and the direction given this diagram. Now, this diagram is a little bit sketchy because that's it should be a perfect circle, but we'll just pretend that's a perfect circle. Okay, so let's first thing that we want to do is we want to extract all of the important information out of this question. Okay, so we got an alpha particle, and we know the charge is going to be positive 2e. Okay, so we know that our charge, which is typically represented with the letter Q, is equal to positive 2e, which is equal to 2 times 1.6 times 10 to the negative 19 coulombs, which is simply 3.2. It's positive 3.2 times 10 to the negative 19 coulombs. That's kind of a number that I like to memorize. Not that you really have to, it's just, why not, you know? Okay, so its mass is going to be 4, it's the atomic mass of an alpha particle is 4, and we know that the mass of, because it has 2 protons and 2 neutrons in the alpha particle, so it's just going to be, our mass is just going to be 4 times the mass of a proton, because protons and neutrons are pretty much the same mass. If you go really deep, they're not, but they're pretty much the same. For most people unless you're going really deep into nuclear physics, you can consider the mass of a proton and the mass of a neutron to be equal. Okay, so our mass is 4 times the mass of a proton, which is 1.66, multiplied by 10 to the negative 27 kilogram. I'm going to do the math real fast. 1.66 times 4. So this is going to be 6.64 times 10 to the negative 27 kilogram. And it's always good to keep your units in base SI units, because it'll make your calculations a lot easier. Okay, it moves in a circular orbit of radius r equals 7.5 centimeters. So r, 7.5 centimeters, and we can convert that centimeters into a times 10 to the negative 2. And that will just make things a lot easier, or we can just convert this to meters basically. So that'll just be 0.075 meters. Okay, just because we want to get base SI units, they work better. The magnetic field has 0.6 teslas, so B field. Why is magnetic field represented with B? Yes, that is why. It just is. So the B field, the magnetic field, is 0.6 teslas. And the magnetic field is perpendicular to the orbit plane, as we might expect. Okay, so these are our equations of interest. Now let's actually look up some more things about the circular motion of stuff, because we know that the force from the magnets, make this a different color to show that we're different things. So magnetic force on moving charge So F as a vector, so FB, and that's for magnetic force. It's going to be Q times the cross product of the velocity and the B field, the magnetic field, and circular motion, centripetal force. Centripetal force is equal to Fc as a vector is going to be mass velocity squared over r. Okay. Yeah, so knowing these, we can solve for b, and once we solve for b, we can solve for v, and then we pretty much can solve the whole thing. So that's what the speed of the alpha particle is. We know that the magnetic force on a moving charge, any charge that moves in a constant magnetic field is going to move in a circular path. And the same force, the magnetic force is going to be equal to the centripetal force. Okay? So, to write that out formally, so magnetic force, centripetal force. So these two are are the things that cause like these are the same force in this case, because the centripetal force is caused by the magnetism. It's just we have two different equations to represent them, and that's going to be quite useful. Okay, so let's write out what we have here. So and I guess we don't really need to worry about the cross product because it is just like a multiplication, because we are in a two-dimensional thing. It's just more formally it is the cross product. But you can just treat it like a multiplication for a 2D example like this. So we're going to have FB is equal to QVB. And that's going to be equal to the centripetal force, which is mass times velocity squared divided by radius. Okay, now we're trying to isolate velocity. Okay, so we can do that by dividing by sending let's just isolate the velocity by doing like we're gonna have like 1 equals m v squared over r q v b. Okay, if we divide both sides by q v b, and what that's going to do is that's going to neutralize the velocity, which is, or it's going to neutralize the square, and then we can just bring everything to the other side except the velocity. So we're going to have r q b over m is equal to v. Okay, now what was our now we had all these values initially, so our r value was, oh, where'd my mouse go? Oh, okay, so our r value was 0.075 meters. Our q value is going to be 2 electrons, but positive, so 3.2. So we're going to have 3.2 times 10 to the negative 16 coulombs. Then our B value, I remember that was 0.6 Teslas. And all divided by our mass, which was 6.64 times 10 to the negative 27 kilograms. Okay, cool. So let's send that into the calculator and figure out what the numerical result of that calculation is. So we got 0.075 multiplied by 3.2 multiplied by 10 to the power of negative 19. Oh, I should write, it looks like a 16, that should be 19. Okay, times 0.6. That whole thing is divided by 6.64 times 10 to the power negative 27. And the numerical result of that velocity is quite speedy. So v is going to be equal to 2,168,674.7 meters per second. Another way that we could write this is v equals 2.168 times 10 to the 6 meters per second, or we can say 2.168 mega meters per second, because mega is another way of saying a million. But this will be how we find the velocity. And is that a reasonable number? It really is a reasonable number, because these velocities will get very, very fast, especially when you have things that are that light. So even like the most minor force on something that costs, or something that's like 10 to the negative 27 kilograms, that's going to be extremely, extremely fast. So that does feel like a reasonable answer. Okay, so cool. This would be the velocity of the particle as it travels throughout the loop. That's awesome. Okay, now we want to find the period of the period of the circular motion. Okay, so let's do that. Period. Circular motion. Okay, so we know that the velocity of this thing is we have the velocity value, and we know that the velocity is going to be always constant as it travels in this circular path around the loop. Always got to be constant. So, and we also know that the radius is equal to 0.075 meters. 7.5 centimeters was the radius of this circle. If we know the velocity and we know the radius, we can figure out the circumference of the circle, and then no, that's just the distance that it travels. So, and every time is going to be the same. So knowing the velocity and the circumference, we can find the period. Okay, so circumference. Let's call the circumference CF. Now I'm not using just C directly because we do have like charge that we used previously, and I don't want the C for circumference to be confused with C for Coulomb, so I'll use CF instead. So the circumference of a circle is 2 times pi times the radius. So we have 2 pi times 0.075 meters. And this is going to give us 2 times pi times 0.075. We get 0.471 meters. So 41 centimeters circumference. Seems reasonable. Okay, so now if we do circumference divided by velocity, we will get the period. Period is often represented with t because it's like the time that it takes for you to do something periodically. Always be the same. So here we'll have 0.471 meters divided by 2.168 times 10 to the positive 6 meters per second. So you can see how the meters cancel each other out. The per second goes upstairs and becomes just regular seconds. And I'm expecting a very small amount of time because that is something very, very big. That is something very, very fast, traveling not a very large distance. So I expect a very small number. So let's do that. 0.471 meters divide by 2.168 times 10 to the power of positive 6. And our result for this is 2.17 times 10 to the negative 7 seconds. And another way that we can write this is 0.217 microseconds. So that's very fast. That's a very short period, but we would expect something like that given that the circle is 7 centimeters and we're traveling at millions of meters per second. We should expect a very small period. Okay, very quick. Okay, and now that kind of so this is going to be t, and that's going to be the second component of our final question, and that is resolved. Cool. So the last question that we have is asking us, given the direction of the rotation, or we have to find the direction at which the positive charged particle is going to be moving in this loop. Basically, is it clockwise? Is it counterclockwise? Now, what we want to do here is, remember how our force was like our magnetic force, our FB, is equal to Q times velocity cross the magnetic field. Okay, so we pretty much we want to be using the right hand rule. So I guess all these vectors are not particularly they're not useless, right? They're there for a reason. So we want our fingers to be going the same direction as V, so it's either clockwise or counterclockwise. We want our fingers to curl. We want our fingers to curl along the magnetic field, and where our thumb points is going to be the direction of the magnetic force. Okay, so if we wanted to start in a clockwise, make my camera a little bit bigger so we can kind of see what's going on. So if we're trying to go counterclockwise on the diagram like this, our fingers would be following V, so like this. Our fingers would curl. Basically, our palm is pointing along the B, and you see how the X's represent that the magnetic field is going into the page. If they were dots, they would be coming out of the page. So we want to curl in the direction that the B is going, so that's into the page like this. So we've going like this, and you can see that the B force, my thumb, which is supposed to be the direction of the B force, is always going to be towards the center. That would suggest that we're going to go that's the direction of the force that it needs to be, because it needs to accelerate you towards the center of the circle to keep you in that circular path. Okay, so it actually is going to be counterclockwise. Because if we were to go clockwise, our thumb would be pointing outside of the circle. So it would be right if it was an electron or a negative charged particle moving through the B field. We'd be going clockwise if it was a negative charge, but since we have positive charge, we're going counterclockwise. CCW. So we want our fingers like this. And they're curling towards the X's. And since the right hand, we have it like this. Thumb points towards the middle. It's got to be counterclockwise. Okay, so it's quite a long question, but quite a beautiful question as well. It ties a lot of subjects together, like magnetic force as well as circular motion and all that fun stuff. Super cool. There is no given solution.